Alright, this video is for lesson 2 of unit 4. We're going to be looking at the graphs of polynomial functions. Alright, so when you see these graphs, the ones that are on the left-hand side are examples of some different polynomial functions, and the ones that are on the right-hand side are examples of functions that are not polynomials. So we looked at these graphs in class and we kind of talked about what we think the characteristics of polynomial functions are. And hopefully as you look at those, you can come to the conclusion that polynomials are always smooth functions. So they don't have jagged points like this one, or this is called a cusp, where it kind of comes up to a point right there, or a jagged point like this. Polynomials are smooth. Sometimes it might look as if it might be a little bit jagged there, but if you zoom in on that, you would see a definite smoothness at the bottom of that little relative minimum there. So polynomials are always smooth, never jagged. Another characteristic of polynomials that you might notice when you're comparing these two groups is that some of the functions over here have more than one part. This one's in 3 parts. This one has also 3 parts if you consider that whole there. Polynomial functions do not have different parts. They are all connected one piece, and the math word that we use to describe that is that it's continuous. It doesn't have any gaps or breaks. So polynomials are smooth, polynomials are continuous. And one other thing you might notice as you're looking at the graphs of these polynomials over here has to do with their range. Every single polynomial function has the same range, and that range is all real numbers. Sorry, I'm supposed to be talking about domain. They all have the same domain, and the domain is always the same for all polynomial functions, and the domain is all real numbers. You can see over here there's a couple that have different domains. This one has a domain of positive numbers. X is greater than 0. This one has some discontinuities in its domain. But for polynomials, you'll always have that domain of all real numbers. So the graphs of polynomial functions are smooth, they're continuous, and the domain of every polynomial function is all real numbers. You can write that with this R symbol, or you could write it like this as well. So we're going to go through some characteristics, or different things we might be interested in with our polynomial functions. Most of these we have talked about before, either in specific cases of radical functions, or we've talked about just with general functions in general, but today we're going to be limiting ourselves just to polynomial functions and how each of these characteristics are with respect to polynomial functions. So the first one I want to talk about is end behavior. In class we did a little sorting activity and looked at some different polynomials, and we categorized the polynomials based on whether they had an even or an odd degree, and based on whether they had a positive or a negative leading coefficient. And as we sorted all of our polynomials, this was what we came up with. And we looked at each of the different categories. So this first category here, if it's an even degree and a positive leading coefficient, we noticed that the end behavior of those functions is all that both ends are going in the positive infinity direction, both ends up, so to speak. So that was true of every polynomial that had an even degree and a positive leading coefficient. And we compared that to the even degree polynomials that had negative coefficients and found that that negative coefficient was in reflection, reflecting it downwards so that now both ends are going down towards negative infinity. So for even degreed polynomials, you'll always see those two ends, the right side and the left side, either both going up if it has a positive coefficient, or both going down if it has a negative leading coefficient. For odd polynomials, or odd degree polynomials, I should say, if they have an odd degree, like 1 or 3 or 5 or so forth, the two ends are not doing the same thing. You've got one end that is up and one end that is going down towards negative infinity. If that polynomial has a positive leading coefficient, then overall it's trending towards going up on the right side. And then, of course, the other side would be going downward. If it has a negative leading coefficient, it just reflects that behavior so that on the right side, these ones are all decreasing. So when we look at a picture of a function, we can always decide what the end behavior is based on looking at that function. But with polynomials, we can actually just look at the equation and decide what the end behavior is based on whether it's an even or an odd degree and whether the leading coefficient is positive or negative. So there's this little chart in your notes that summarizes that, but let's look at it in the context of some problems. So this function f of x is negative 1/2 x to the 4th minus x to the 3rd plus 3/2 x squared plus 7x minus 12. It's a lovely function. If we wanted to know what the end behavior of this function is, we first just need to note that the degree is 4, which is an even number. Even degree polynomials either mean both ends are going up or both ends are going down. So we have to decide which of those two cases we have here. Well, the leading coefficient of that polynomial is negative 1/2, which is a negative number. That tells me it's this one. They're both going downward towards negative infinity. So as x goes to the right-hand side, the function is going down. As x goes to the left-hand side, the function is also going down. So we can decide what the two ends are doing without even looking at the graph. Now I'm going to show you the graph just to confirm that we were correct. And there it is. Both ends are indeed going down, so we were right about the end behavior. Now if you're absolutely stuck, you could try graphing it to get your answer as well, but it's a lot faster if you can just get used to looking for that degree. It's definitely valid to check your answer though by looking at the graph. Here's another function. f of x is x to the 3rd power minus 6x squared plus 5x plus 12. So we look at the degree of the function, it's degree 3, which happens to be an odd number. So that means either we have the right hand going up towards positive infinity, or we have the right hand going down towards negative infinity. So we look at our leading coefficient to decide, and our leading coefficient for this polynomial is 1. We have 1x to the 3rd. 1 happens to be a positive number. So that means that we want it to be going up on the right-hand side. So that would be the correct one. And I often draw that little picture of the two ends to help me. You definitely don't have to do that, but I like to do that. So we want to know for this notation that what's the function doing as x goes to the right? Well, on the right-hand side, this is going to positive infinity. What's the function doing as x goes to the left towards negative infinity? Well, in this case, the function is very low over there on the left. Here's a picture of the function, so we can just sort of confirm that we were right, and that looks good. On the right, it's up high. On the left, it's going down low. All right, a couple more to try. In class, students did this and then just checked their work. So if you want to pause and just check yourself, you can. X to the fifth is an odd degree, and we have a negative leading coefficient here. That means our end behavior is negative on the right, and it's odd, so the two ends are doing opposite things. So on the right, it's going down. On the left, the function is up high. Hopefully you got that. Here's a picture of it. For the next one, this is an even degree, and that leading coefficient is positive. So our function should look like this on the two ends. So on the right, it's going up, and on the left, it is also going up. And here's a picture of that function so that we can just confirm that we were right, and it looks exactly like we thought it would. All right, so that's it for end behavior. So I want to remind you that we have talked before about relative extrema. Sometimes they're also called turning points. And let's see, we also talked about that sometimes you will see the word local min or local max instead of relative, and they mean more or less the same thing. So here's a graph of a function. If we look at this function, you can see that it has a relative minimum. Remember, a relative minimum is a low point on the graph. It isn't the lowest point on the graph, it's just a low point, and here it is at the point 3, negative 8. And I do prefer it if you write that as a point. And the relative max, or the high point on this graph, or a high point on this graph, would be the point 1, 0. And remember, they can have more than one of these relative mins or relative maxes. You just look at the function, and based on that function, you decide. We've also before talked about intervals of increase and decrease. Wanted to refresh that with you. Remember, when you're working with intervals of increase and decrease, you are thinking about portions of the domain, so make sure you're using x values and really focusing in on that x-axis. Don't ever pull a y value for an interval of increase or decrease. And you should read the function just like you would read a sentence from left to right. So we'll start with this far side from negative infinity, and here's its turning point, so that's where it switches. From negative infinity to 2, that's an increase. The function is growing during that portion. So from negative infinity to positive 2, we have an increase. Then the function turns at that minimum, or relative max, sorry, and then it decreases between the values 2 and 4, so that's an interval of decrease. And then it has that relative min, and it turns around, and from 4 to infinity, it increases. Remember, if you have two sections like this interval of increase, you should use the union symbol between those two intervals. So that's the interval of increase and decrease for this function. We did that in class. I'm going to skip that for these video notes. So also wanted to just remind you about intercepts. I'm sure if you're looking at this function, you can immediately tell me what the x and y intercepts are. The x-intercepts, and this function has 4 of them. Sometimes we'll see quite a few of those x-intercepts. Negative 4, 0, negative 2, 0, 1, 0, and 3, 0. Make sure you're listing the entire point for the intercepts. And the y-intercept of this function is here at 0, negative 1. So that's not anything really new to you, but I wanted to talk a little bit about polynomials and some different behaviors we can see at those intercepts. Oh, sorry, first, I'm getting ahead of myself. First, I wanted to talk about that when we're talking about polynomials, sometimes x-intercepts can be referred to as the zeros of the function. So the reason that they're called zeros is because they are the x values that cause the function to be equal to 0. So -2 is a zero of this function because it causes the function to have a y value of 0. 1 is a 0 of this function because it causes the function to have a y value of 0. So if I ask for the x-intercepts, I definitely want you to list those points. But if I ask you for the zeros of the function, it is fine to just list those x values. The zeros of this function are -5, -2, 1, and 3. It has 4 zeros. And we will talk more about that in the next lesson. Another thing I wanted to talk about is when you see some interesting or different behaviors. So these are two polynomials that you can see in blue and in green, and they each have 3 x-intercepts. For this blue function over here, we have an intercept at -4, one at -1, and one at +1. But you can see at each of those 3 intercepts, the function is behaving a little bit differently. At this first intercept, -4, it's going downward, so it's decreasing, and it almost flattens out for a second, and then it continues downward. All right, when we see that sort of behavior on a polynomial, that intercept is terracing. We use the word terrace to describe that behavior. They use the word terrace also in a lot of other contexts, like terrace farming is when you sort of cut back into the hillside to get a flat area to farm. So the terracing is when it flattens out like that. We will talk about what causes that behavior next class period, but I just wanted to introduce you to that terminology today. This intercept right here at -1, that's just a regular intercept, just like we've always seen, where the function just passes through that point and continues on its way, didn't flatten out or anything. And then one other type of intercept behavior that we'll see with polynomials is when the function is decreasing or increasing, and it absolutely hits that intercept as expected, but then instead of continuing to the other side of the x-axis, it turns around. It still has an intercept there. That behavior is called a tangent behavior. That intercept touches the x-axis and turns around. So watch for those two types of behaviors and you'll see them. Again, this one where it flattens out is a terraced intercept. That middle one is regular, and then we have over here a tangent intercept. This green function has a couple of different behaviors happening as well. So you can see right here at -2, that's a terrace. It flattened out for a second and then continued down. And then it has 2 tangent intercepts right here at 1 and at +5. Touches the axis, turns around. Again, we'll talk more about those and what causes that behavior in the next class. Also, with respect to the y-intercepts, it's nice to be able to determine what the y-intercept is, not just from a picture of the function, but also from an equation. So here's an equation, f of x equals x to the 6th plus a lot of other stuff. If I want to know the y-intercept of that function, and I do have a graph of it, but the y-axis is not scaled, if I wanted to know what is the height of this y-intercept right here, remember that if you want to know the value of the y-intercept, it always occurs at the x value 0. So if we want to know it from the function, we can just substitute 0 in for x. F of 0 is 0 to the 6th plus 11 times 0 to the 5th plus 35 times 0 to the 4th plus 5 times 0 to the third minus 100 times 0 squared. And probably so far you've been able to do that in your head. Minus 16 times 0 plus 64. Well, that's a whole lot of 0 plus 64. The y-intercept of this function happens at the point 0, 64. I need a finer pen. There we go. So it has a height of 64. In standard form of a polynomial, you'll see that that is going to always be that constant term at the end of the function if it's in standard form. All the other terms, when you substitute 0 in, they immediately become 0. So it's not very difficult in standard form to find the y-intercept of a function. In intercept form, if you have a factored form of the function, it's a little bit harder to determine that y-intercept, but again, it still happens at the x value 0. So we can substitute 0 in for x. In this case, we have negative 1/25. This becomes 0 minus 1, so that's a negative 1 squared. This becomes 0 plus 2, so that's a 2 to the third. This becomes 0 minus 5, that's a negative 5 squared. And if you calculate that, whether it be in your head or via your calculator, you'll find that that is negative 8. So the y-intercept is at the point 0, negative 8. You can find these intercepts from your calculator. Here's some rough instructions for how to do that. If you're interested in using the TI-84 to find those intercepts, I would be happy to show you how to do that. I'm not going to bring it up on my screen for the video though. But you're more than welcome to ask me how to do that in class, or if you've used your TI-84 a bit, this probably would be enough to help you. You're using in both cases the calculate function, which is the second button over from the right-hand side on the very top row. And we have used that before in class. All right, so that is the functions of polynomial, or the characteristics of polynomial functions. Again, we'll be continuing to work with these graphs of polynomial functions for the next couple of lessons. Thank you.